In this video, we're going to map out the wiring scenarios you might run into with 2, 3, 4 wire RTDs and 2, 3, 4 wire transmitters. Sometimes that can get all jumbled up. So I think the way to navigate all that is not by flipping through schematics and memorizing diagrams. It's if you get what's going on at the fundamental level, you can keep it all straight. So that's what we're going to try to do here. So an RTD is just a resistive device. RTD might stand for a resistive thermal device or resistive temperature detector, but it's just going to be made out of metal, which has a positive temperature coefficient, and you're going to have the probably the most common things like a very thin platinum wire, perhaps. That way it's mostly immune to corrosion and things like that. So typically, maybe 100 ohm platinum wire might be one you'd run into, but that's what you're going to have sitting right here. Now the resistance is going to vary with temperature, just as metal does. You're going to power up the RTD with a constant current source. So as you flow constant current through a varying resistance, you're going to get variable voltage that's measured here. And the variable voltage is going to represent the varying temperature out here. So to trace it through, as temperature varies, the resistance of the metal varies. As the resistance here varies, current we're holding constant. So with Ohm's law, of course, current's not going to change because we're holding that with a constant current source. And then your varying resistance with constant current gets you your varying voltage, and that represents the temperature. In this example, we then take the voltage that's coming from the RTD, which represents temperature, and we take that voltage, and with a microprocessor, you would take the representative voltage that represents temperature and convert that to a 4 to 20 milliamp signal that represents temperature. And there's some scaling options. Oftentimes, this would be the transmitter's job to take the voltage coming from the RTD and convert that to a 4 to 20 milliamp signal. So for our examples in this video, that's what we're going to look at. We're going to look at a typical setup where you might have temperature being sensed by an RTD, converted to a varying voltage, then converted by the transmitter to a 4 to 20 milliamp signal. Altogether, you have varying temperature, converted to varying resistance, converted to varying voltage, converted to a varying current. The RTD is just a two-terminal device fundamentally, just either side of a 100 ohm platinum wire, for example. But there is one small problem with that. If you're trying to look at the voltage back that comes back to the transmitter, which we see here, this voltage technically includes the voltage drop that would occur along this wire, and also the voltage drop that would occur along this wire. So technically, this voltage that the transmitter is reading is not this voltage right across the RTD. Now it's very close, but and in some cases that might be fine. That little bit of error is not a big deal, but in other cases it is significant. The IR drop along this wire, because remember, we're running current through this wire to get to the RTD, and we're running current through this wire to return. So you do have an IR drop here, and you do have an IR drop here, which add to the voltage that's actually across the RTD, and that would be a source of an error. How is that error significant? If it isn't significant, then a 2-wire RTD connection is just fine. If it is significant, let's show you how we solve that. Here in this diagram, you can see we solve it with a 4-wire connection to the RTD. Now the RTD is still fundamentally, it's just nothing changed. It's still just its 100 ohm platinum wire from here to here. What we've done though is we've gotten our constant current source to provide current through this wire to the RTD and then return the current through this wire. But to look at the voltage for the microprocessor in the transmitter, to actually look at the voltage, we've run 2 separate wires right out to the RTD, and notice these 2 wires are really just for the voltage sensing of the RTD. So this is very high impedance here. There isn't current to speak of running on this wire or this wire. So since there's really no significant current running along this wire, there's no significant IR drop. So essentially the voltage at this point will come right back here, and right here the voltage will be the same all along that wire. So we're really getting a better, more accurate look at the voltage that's actually across the RTD. So it gives you just that extra bit of precision if you need it. And if you step back and look at this 4-wire RTD, it's important that you see the simplicity of it. Essentially, these 2 wires, like if you just look at the raw RTD, let's say you just buy an RTD, you get it shipped to you, you open the box, and it would have 1, 2, 3, 4 wires. It's important right away that you understand that 2 of the wires are identical, and another 2 wires are identical. So always keep that simplicity in mind. It actually doesn't matter which wire you use here. For example, I think ones we have in the lab, you might have 2 white wires and 2 red wires. And you don't need to waste time trying to distinguish which red wire you should use to carry current to the RTD and which white wire or which wire is which. It helps save you time if you just realize right out of the box that the 2 white wires are identical. They're going to the exact same place. And the 2 red wires are going to the exact same place. Which probably raises a question in your mind, or in some people's mind when they're hearing that. Right away is you might get asked, well, why do you need 2 wires going to the same place? And with that gets back to the fact that one of those 2 is going to carry current to the RTD, while the other one just comes in to look at the voltage at that point. So the subtle distinction between like the 2 white wires, for example, there is no distinction until you connect it to what you're going to connect it to. The distinction is then when one's carrying current, it's the current carrying white wire, and the other one is just the voltage sensing lead. Another nice thing about understanding these basics is maybe out on the plant floor you've got a 2-wire RTD connection, and the RTD that you're pulling out of the box is a 4-wire RTD. That's no cause for panic, right? A lot of times you'll get the universal maybe 4-wire RTD because if you have extra wires, so what? That's not a problem. It doesn't mean you have to use them. So you can have a 4-wire RTD and use it with a 2-wire connection. Not a big deal, right? You just have 2 wires that you're not going to use. So just use one of the white wires. You wouldn't use this wire. This would not be used. And you wouldn't use this red wire. So a 4-wire RTD is universal. You can use it as a 4-wire or a 2-wire. And now I'll show you one more option, and that would be the 3-wire connection of an RTD. And so a 3-wire connection for an RTD simply comes from the fact that people figured out that probably any IR drop that's occurring on this wire that's carrying the current to the RTD is symmetrical. Assuming the wires are the same gauge, the current is identical, and assuming they're close to each other, the temperature conditions of the wire will be the same. So it's a fair estimate to say that whatever IR drop you have on one side is the same as the other side. So for that reason, you don't necessarily need 4 wires. You can do a 3-wire RTD connection, which means you'll need the 2 wires that come to and from the RTD that carry the current, so the constant current, and here's the wire carrying it to and from. So those are 2 of the wires. That's the 2-wire connection. Then just one more wire, a 3rd wire, can come out here to this point, and what you're going to have is a voltage that you can see between here and here that is representative of, it is the IR drop that you're looking at from one side, for one side. So that's V2. So just double that and subtract it from V1. In other words, here's V1 that includes the IR drop on both sides of the RTD plus the voltage of the RTD. So V1 has the IR drops in it, and you want to get them out, subtract 2 times one side's IR drop. So that's the 3-wire connection. And again, if you have a 4-wire RTD, no need to panic, right? You're just going to need 3 of those 4 wires. The extra wire here, cut it off, tape it up, whatever. You don't need it. But a 4-wire RTD is very generic and very useful because you can do, if you have 4 wires coming off of your 100 ohm platinum wire, for example, if that's what you have, you can use just 2 of those 4. You can use 3 of those 4. You can use all 4. And the choice would be, what is your transmitter wanting? What input is your transmitter looking for? Is it looking for just 2 wires? Is it looking for 3? Is it looking for 4? That's what dictates whether you use a 2, 3, or 4-wire connection from your RTD. It's what your input to your transmitter calls for. What type of transmitter input do you have? And once you have your RTD interface to your transmitter, the transmitter then does its thing. It takes the voltage that represents the temperature, scales it to a representative 4 to 20 milliamp signal. And that's what we'll talk about next, because there's several different types of transmitters when you're looking at this 4 to 20 milliamp output of the transmitter. We talked about the input side of the transmitter. If it's an RTD input, we just wanted to clear up the 2, 3, 4-wire connection to the input of the transmitter. Now we're going to talk about the 2, 3, 4-wire output side of the transmitter, and you can see why the fundamentals are important to sort of nail down, because you got 2, 3, or 4-wire connection options on the input of the transmitter with the RTD type input, and you'll see now we got 2, 3, 4-wire connections on the output side of the transmitter, and that can all get tangled up in some people's minds and in some people's documentation when they start talking about the transmitter just generally, and you got to really know what are you talking about, inputs or outputs and so on. So we'll look at the output side next. So a 2-wire transmitter is getting its name because it's just 2 wires that need to be connected to the output. So we're talking about the output side now. Also known as a loop-powered transmitter. Notice there's no power that has to be supplied. In other words, if some transmitters, you might have to bring 24 volts to power the transmitter. So you'd need some kind of power supply coming to the transmitter. So this is not that. We'll get to that. That would be a 4-wire transmitter. But a 2-wire transmitter, just 2 wires needed for the output signal. And it's a pretty cool trick. I mean, it's getting its power. I mean, there is a microprocessor inside here that does need powered. And it's going to steal its power from the 4 to 20 milliamp loop, which means if that current would be as low as 4 milliamps, you can see the circuitry in here has to run on that. That's all it's going to get. So yeah, it's going to be a very low powered design, and but yeah, that's the only power it can steal is from whatever current's running through the loop. It'll steal some of that power to run its own circuitry. So it's a pretty cool trick. So it might be known as a 2-wire transmitter. It might be known as a loop powered transmitter. It's stealing its power from the current loop. And I like to emphasize the fact that what is going on in a loop powered transmitter or a 2-wire transmitter is you have basically inside here, inside the box, is a current regulator, a constant current regulator, as opposed to a current source, which is what a 4-wire transmitter, when we get to that, is going to look like. That should help you really get a clear picture of what's happening. That distinction between current regulator and current source, I hope is the thing that will pop into your mind when you're trying to wire one of these up. So a loop powered transmitter, a 2-wire transmitter, behaves it is a regulator, behaves as a regulator in line, in series with the current loop. It doesn't matter what order these things happen in, are positioned in. So let me show you that. What do we have? We've got you do need 24 volts to do the pushing. So we've got that. And then you're going to have in series, maybe we'll go here next. This would be your PLC input. So it's going to receive the 4 to 20 milliamp signal. And your positive side of your PLC input is here. And your common, if it's single-ended, you'd have your common here. If it's differential, it'd be the negative side. But your 4 to 20 milliamp input for your PLC, with this polarity, it's going to be sitting here, and the 4 to 20 milliamp signal is going to be running to that input to be seen by the PLC. It'll be terminated with a resistance and converted to voltage and then converted to a digital number, with a A to D converter and all that. But yeah, here's your 4 to 20 milliamp input to your PLC. And look how we have everything in series. We'll get over to that in a minute. So remember, way over here, you've got temperature causing a varying temperature, causing varying resistance, causing varying voltage, which microprocessor converts and scales to a varying current. That varying current is sent to the PLC to then have an idea of what the temperature is, and it'll convert it back to a number for your PLC program. So here is the milliamp current that represents the temperature. And it's all in series with a loop powered transmitter. Everything's in series, and it has to be in series aiding. You can't have things fighting each other, so the polarities are important. So watch as we trace. The conventional current would be flowing right this way, and here you go. Conventional current is coming into the regulator. It's getting regulated so that it's representative of the temperature, and it's flowing out. And you can see as you trace that you have to be, conventional current enters, so that's the positive side, and leaves, and here you're back to your source. So here is your source. So conventional current leaves the positive side of a source, but as it runs into things, the side that it enters is positive. Remember that from way back in the DC course. So conventional current enters, so that's the positive side, and leaves, that's the more negative side. Conventional current's going to pile up when it hits some kind of an impedance. It will always be the more positive side on the entrance to that impedance, if it's positive charge that's flowing, right? Just like rocks in a stream. So you've got this polarity that's very important. When you're wiring it up, you have your source. The three things you're trying to put together are a 24 volt power supply, a PLC input, and a loop powered transmitter output. Those are the things you got to put together. And it doesn't matter what order you put them in. So that's important to understand. They can be in any order, but they must always be in the right polarity. So again, just trace these through. Notice for the loop power transmitter, you're going to have the negative polarity of the output going to the positive polarity of the PLC input. Negative to positive, and so on. And that's a big distinction. When we get to the 4-wire powered transmitter and it behaves like a current source, it won't look like this. It won't be the negative output of the regulator going to the positive side of the PLC input. In fact, it'll just go straight across. It'll just source current, positive to positive, negative to negative. So we'll get to that. But just so you know, those are the big distinctions when you're trying to wire this stuff up. If you have a loop powered transmitter, you can look at this drawing to help you get that in focus. But it's going to be this, series type loop, as opposed to with the 4-wire transmitter, you're going to have a current source sitting here and you just come straight across. So it's a parallel configuration right from your transmitter right across to your PLC input. We have a drawing for that we'll bring up in a minute. Just a couple variations on the loop powered transmitter. If you have single-ended inputs on your PLC, or sometimes you have it's in the instructions that whatever the PLC power supply is, you have to have the negative side of the input of the 4 to 20 input has to be tied to that same common. So you might have something that looks like this, where your PLC power supply is shared, the 24 volts. So this just it's basically the same thing that we were looking at, but just a couple things to point out that this connection here might need to be there. Another variation on the loop power transmitter, you might see a dedicated power supply here for the PLC, and a separate power supply maybe to be the loop power to power the loop. I mean, this wire here might run all the way out, on the plant floor or something like that. So there might be reasons to use a separate supply in case something happens out here to damage this. But and I mean, speaking of the hazardous nature of the out there on the rough and tumble area of the plant floor, you might have an analog opto-isolator sitting here too. So, I mean, just so you know, that you might see a couple other things. It's still loop powered, even though you have a separate power supply for the PLC and a separate power supply for the loop. You can see that. And then they all share a common because of the nature of this PLC input, if it's a single-ended input. If it's a differential input, I'd have to think about that. But they're probably, I'm thinking there might be a couple other subtle variations that you might have to deal with. For a differential input, you still have to put everything in series. So you just have to map it out. But for a loop powered, you think series circuit. And if you want to check the current in a current loop, of course, remember, current's the same everywhere, so it doesn't matter where you would look. You can look here, 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 here. So anywhere you want to break into the loop and have a look at the loop current or monitor the loop current is fine. It's a series circuit, current's the same everywhere. So then a powered transmitter, like we've mentioned, does get its own power. So you'd have a 24-volt power supply that powers up the transmitter itself. That's here, right? It's a 4-wire transmitter, also known maybe as a powered transmitter. Not loop powered, but it has its own power. And that's why it's a 4-wire connection to it. You got to bring 24 volts to it. And this is the distinction I like to keep in my head. What I have inside here is now a current source, a constant current source. And you can see it's going to be the microcontroller in here that's taking, again, you know, the temperature variation that causes the resistance variation that causes the voltage variation. It's going to take this voltage variation and create a 4 to 20 milliamp current, but it's going to create it as a current source. It's not going to create that 4 to 20 milliamp signal by regulation as something in series. It's going to create it as a constant current source. So 4 to 20 milliamps, 4 to 20 milliamp constant current source, and the connection is pretty straightforward, right? It's not a series circuit now. It's just going to bring that 4 to 20 milliamps right over to the PLC input with a return path. So it's a parallel connection now, and notice the big difference. If you have a powered transmitter or otherwise known as maybe a 4-wire transmitter, your 4 to 20 milliamp signal, the positive polarity of the output of the transmitter goes to the positive polarity input of the PLC, and negative to negative. Very different, right? Than the loop power transmitter, which took the negative side of the transmitter output to the positive side of the PLC input, this to this. So that would be a classic mistake, you know, that people would make, you know, on a loop power transmitter. They would just think plus to plus, minus to minus. But I hope, as you know, of course, life's not always that simple. So there we go. But here it is straightforward right across. So those are probably the big distinctions between loop powered versus powered transmitter, or 2-wire versus 4-wire. This connection here shows up as very different. And here you could have a separate power supply for the PLC, you know. And here with the powered transmitter, of course, everything stays pretty easy to see. I mean, it's you could put an analog opto isolator right here. Maybe not opto, maybe transformer isolation, but whatever type of isolation, but that would be a typical thing to see. And everything stays pretty simple as far as the drawing goes. And nicely isolated. You can see that, right? You got your separate 24 volts out here. You got your isolation here. I think you can see you've done a nice job of isolating the PLC from the rough and tumble world that's going on out here. If you don't have differential inputs on your PLC, you might have more of this. Things start getting a little bit less isolated, of course. You start having to tie things in here with a common. You could get your isolation, though, if you put your 4 to 20 4 to 20 milliamp isolator here. That would work. So you could still maintain. But this would be more of a single-ended input look. And another little variation, I mean, you can use the same power supply. You don't have to use a separate power supply to power up your transmitter. So you could conceivably use the same 24 volts to power your PLC and power your transmitter here. And the transmitter, when we're talking about transmitting, it belongs over to this side. I mean, you're transmitting the temperature that's been converted to a 4 to 20 signal. You're transmitting that back to the PLC. That's what we're not transmitting from the PLC out to here. We're transmitting from the sensor to the PLC. And finally, you can have a 3-wire transmitter. All they're doing is sharing the common. So it's still a constant current source. The transmitter does get powered by 24 volts, and here there's that wire. So you're bringing 24 volts to your transmitter to power it up. And the transmitter is a constant current source that's going to generate a 4 to 20 milliamp signal, and that's available here. And then all they've done is used the common side of the transmitter and the common side of the PLC input as the same wire. So I think you can see the current source is still going to run a 4 to 20 milliamps that represents temperature to the PLC and return it to itself. So the return path for the 4 to 20 milliamp signal is the same as the return or the common for the power, the 24 volts power. See how that's all still. So the powered transmitter, I mean, it's still a powered transmitter, but they're sharing this common as far as bringing power to the transmitter and also a return path for the 4 to 20 milliamps signal. It's still a constant current source. So it's very much in the same category as the 4-wire transmitter. They're just sharing the common. That's all. It's still a constant current source. It's still a powered transmitter as opposed to a loop powered transmitter. It's not that. So if you only have 3 wires, there you go. That's what's happening. And again, some variations. You might need to tie PLC Common to the common if that's stipulated in the PLC documentation. And again, you could conceivably run it all off of a single power supply. That would be an option if you wanted to. So that wraps up 2, 3, 4-wire RTDs and 2, 3, 4-wire transmitters. And just in conclusion, I just wanted to show if this 2, 4-wire thing sounds like it's ringing a bell, there are other types of measurements that use this same concept that we've seen with the RTD, for example. So like a 4-wire resistance measurement you might have run into, or with a bench DMM where you have maybe test leads that are going to be able to do this for very low, a device under test that's a very low resistance, and you don't want to include the resistance of the test leads. Very simply, you can have an ohm meter. All ohm meters, what they do is send out a constant current and read the voltage and then use Ohm's law, So they'll send a small current through whatever you're trying to measure, as far as you're trying to measure a resistance of something, send a small current through it and then measure the voltage that develops across it. But the problem, of course, is you don't want to include the voltage across your test lead wires. So you do the same thing that we saw with the 4-wire RTD. And in fact, highly accurate ohm meters that are able to measure very low resistances, this is what they're going to do. They're going to have a test probe that actually has it looks like 2 leads, but inside there's 2 wires in each lead, and there's 2 wires going to the same place, which again makes you think, well, why? And here is the why that we mentioned way back at the beginning of this video. The why is because 2 of the wires are going to carry current, and 2 of the wires that also are redundant, it seems, they go to the exact same spot. But these 2 wires do not carry current. So you've got your voltage measurement inside your ohm meter that can just have a look at the voltage way out here and not include any kind of voltage drop on the wires. So you're going to have a 4-wire resistance measurement is what they would call it. And you can buy special test leads that they don't look any different here. It just looks like a single lead, but there are 2 wires inside it. And at the point of the probe, it doesn't look any different. There's just 1 probe tip. Back here, it looks different. You have maybe 2 banana jacks that need to be plugged in. And again, 2 banana jacks that need to be plugged in. And one gets plugged into the current source and one gets plugged into the voltage measurement that the ohm meter is using. So if you've seen those, now you understand maybe what's going on. It always looks a little strange because you've got 2 banana jacks here and 1 probe tip here. Yeah, and you're wondering, or if you're like me, you're wondering, like, why do I have 2 banana jacks for 1 piece of metal, 1 point of metal here? And this is why. And I can dig some of those out. We can have a look at those. And maybe one other example that kind of is in this whole family of 2-wire, 4-wire. It's possible you have a power supply that has what's called sense leads. So maybe you have your voltage output of your power supply, and you need your load to get exactly 24 volts, let's say. So 24 volts might be generated here. But of course, there could be a little bit of IR drop as you're carrying current on these wires for your load. So 24 volts here, but maybe only 23.5 volts gets to the load because maybe you have a 1/4 of a volt drop on each wire. what'll happen is your sense leads are run out to where your load is, and your sense leads will see that only 23.5 volts are getting to the load because of the IR drop here. And so the sense leads will report that back to the power supply, which will boost its output to 24.5 volts. So now your output is 24.5 volts here, but at the load, it's exactly 24 coming back through the sense leads, and they're reporting 24 volts. So the power supply will adjust its output to whatever's necessary to get the voltage you want. If you set it for 24, it's going to watch for 24 to show up at the sense leads and adjust the output to be whatever it takes to get that. So these types of power supplies, you'll see that they'll be marked just like in the drawing here with S plus and S minus. If you're not going to run sense wires out to your load, you do need to jumper this sense lead over to here. So you'll see them jumpered maybe right out of the box. You can't leave these open. If you leave S plus and S minus not connected to anything, that power supply is not going to see any voltage being reported back. It's going to crank the output as high as it can to try to get voltage to show up on the sense leads. So keep that in mind. If you have a power supply output that has sense S plus and S minus, S plus has to be connected to V plus. Even if you don't, especially if you don't connect it out here, if you're not planning to use the 4-wire connection to your load, well, you better then jumper it from here to here and jumper it from here to here. So, okay, hopefully that helps you with the 2-wire, 4-wire tangle. Hope you don't get it tangled up now that you know these basics that lie underneath it.